Okay, we've been talking about solids. We're going to look at ionic solids in this section. So we looked at a bunch of different types of unit cells for crystalline structures. And many ionic compounds do have structures similar to those. The thing about the ionic compounds is you've got two different kinds of ions, a cation and an anion. And so that changes the structures a little bit. So when we're talking about an ionic compound as opposed to an atomic solid, the coordination number is going to represent the number of close cation-anion interactions. So the positive and negative ions, how many close interactions there are. The more of those interactions, the lower the energy, the stronger the crystal. If the cation and anion are similar in size, they compact together better than if one is much larger than the other. So the crystal structure that actually forms balances a number of things. It balances a coordination number, trying to get the highest coordination number. We have to have charge neutrality. So if you need two chlorides to balance the charge on your calcium, that's going to affect the crystal structure. And then different ion sizes are going to mess around with that as well. So when we have ions that are similar in size, such as this compound cesium chloride, the chloride ions will typically occupy the lattice sites of a simple cubic cell. So here we have the chloride ions in a simple cubic cell. The cesium is a different ion, and so this is not body-centered cubic, because in body-centered cubic, this would be a chloride also. Okay, so you can when we determine what structure these are, we're looking at one of the ions. So this would be simple cubic. The cesium is in between, in the middle of the cell. So this has a coordination number of 8 because this cesium is in close contact with 8 chlorides. Each unit cell contains one chloride ion and one cesium ion. Calcium sulfide is also a 1-to-1 ratio of cation to anion with similar sizes, and it's going to have a similar structure. If ion size were the only consideration when we have compounds with different ion sizes, if it was just the ion size, with sodium chloride, sodium is a very small ion and chloride is much larger, and so we could fit a lot of sodiums around the chloride. But it has to be charge neutral, so we can only have one sodium ion for every one chloride ion. So we have to have an equal number of each. So that will end up with this structure where we have a coordination number of 6. So if we look at the sodium ion, it's in contact with 1, 2, 3, 4, 5, 6 different ions. So the coordination number is 6. The chloride ions are occupying a face-centered cubic structure. So here's part of the unit cell, one face of it, and there's a chloride ion in the middle of it. And here's another face, and there's a chloride. So it's a face-centered cubic. The sodium ions are in between the chloride ions. This is also called a rock salt structure because it's the structure of rock salt. And in the unit cell, you have 4 cations and 4 anions. If we have really large size differences, then the coordination number is lower. Here, the sulfide is so much bigger than the zinc that the face-centered cubic ends up looking a little bit different. This is called a zinc blend structure. So we've got the sulfide ions in a face-centered cubic, but now the zinc ions are arranged differently. You see this one, how it's all nice, like a grid? Everything's right angles. Here we've got the zinc ions occupying what's called a tetrahedral hole in that structure. So if you look at 4 of the sulfide ions, they make a tetrahedral shape, and then there's a hole in the middle, and that's where the zinc ion is. So this also has a unit cell with 4 of each kind of ion, but here the coordination number is 4 instead of 6. Things get even more complicated when you have unequal numbers of ions. So the ones we looked at so far were all a 1 cation to 1 anion. If you have a 1 to 2 cation to anion ratio, many of these compounds adopt the fluorite structure. Fluorite is calcium fluoride. So here we've got calcium ions in a face-centered cubic structure, and the fluoride ions are occupying all 8 of the tetrahedral holes. In the zinc blend structure, the zinc ions were in 4 of the 8 tetrahedral holes. Because this is a 1 to 2 ratio, the fluorides are occupying all 8 of those holes. So we've got 4 cations and 8 anions. So that's the fluoride structure, and then the anti-fluoride structure is a 2 cation to 1 anion ratio. So it's just sort of the opposite. Exchange the cations and anions. So which compound is most likely to crystallize in the zinc blend structure? Well, we got to remind ourselves, what is the zinc blend structure? Because we just heard about it, right? So that's fluorite. This is zinc blend. So in the zinc blend, we have a 1 to 1 ratio, 1 cation to 1 anion, and we have a large size difference. So that's the sort of thing that's going to tell us what structure to predict. We are only covering a couple of the different structures. There's a whole lot more. And it's a very interesting field, but we're just going to scratch the surface. So as we look at these 3 choices, one of them is pretty easy to eliminate. B. It can't be B because magnesium chloride has a 1 to 2 ratio. So that's not going to work. That would probably do the fluoride or anti-fluoride. So it's not that one. So then we're selecting between rubidium chloride and copper iodide. What we're going to do is we're going to compare the sizes of the ions. Here we've got 148 and 181. The chloride's bigger, but not terribly much. And here we've got copper 96 and iodide 216. So this is a larger size difference, so it's probably C. This one, rubidium chloride, is probably going to do the rock salt structure because the ions are more similar in size. Any questions? Yes? You'd have to figure it out on an exam. Yeah. This is one of those topics that it's important for everybody to have heard about and thought about a little bit. I would only expect an A student to get a question like this correct on the exam. If you're not trying to get that high A, this is a topic that you can just do the homework on, and don't stress about trying to memorize the names of the structures or anything. It's not a big deal, right?